today we shall consider the Turing machine as a generating device. We have considered Turing machine as an input output device computing something, and we have also looked at the Turing machine as an accepting device, accepting type 0 languages. We can have a Turing machine where there is an output tape, other tapes are there, but there is an output tape, the Turing machine, and in this output tape strings are printed within hash marks. Some strings are printed on this tape, and this tape head always moves right, and something written once is not erased, it is blank towards the right. First it writes a hash symbol, then some string, then hash symbol, then another string, hash symbol, and so on. So, whatever is appearing between two hash symbols, that string is said to be generated by the Turing machine. If this Turing machine is denoted as M, then G of M, we usually denote acceptance by T of M or L of M, usually by T of M. The language generated by this Turing machine using an output tape denoted as G of M is W. W is generated by M. What this means is this W will appear between two hash symbols in the output tape. The set of all strings is denoted by G of M. Now, there is no necessity that the string should be generated in any particular order. We know what is meant by a standard ordering on strings, lexicographic ordering on strings, all those things we know. It need not be in any particular order, and it is also not necessary that one string should be generated only once. So, W1 is generated here, after some time it may again be generated, does not matter, there is no such restriction. Strings are generated between hash symbols, and all such strings belong to GM, and it is not necessary that they should be generated in any particular order. Longer strings can be generated first, shorter strings later, and so on, and also one string may be generated many times, does not matter. But if the strings are generated in the standard ordering manner, lengthwise increasing and within the same length in the lexicographic ordering, then that language is a recursive set. What is a recursive set? A recursive set is a set accepted by a Turing machine which halts on all inputs. Okay. So, we get these two characterizations now. So, the first thing is we want to show that if L is equal to L of M1 for or T of M1, I use the word T of M1 for some Tm M1, if and only if L is equal to G of M2 for some Turing machine M2. That is, if L is accepted by a Turing machine M1, then L is generated by some other Turing machine M2 and vice versa. Okay. So, we have to prove in two directions. So, L is equal to T of M1, then construct M2. Then the other way around, L is equal to G of M1, then construct M1. So, the second portion we will take first, this is one, okay. So, second is L is equal to G of M2, then construct M1. Now, how do you go about this? You have a Turing machine, it can have many tapes, but one output tape where strings will be printed. Now, how do you construct M1 which will accept the same language? M1, M2 has all this, M1 will have one more input tape, input is kept here, M1 has all this plus the input tape, M1 simulates M2 and it generates one string. When a hash symbol appears, up to the point where one hash symbol appears, M1 simulates M2. Then when a hash symbol appears, M1 compares this string generated in the end, last string generated with the input. If they are the same, it will accept. If they are different, it will proceed further. If they are the same, it will accept, otherwise it will generate the next symbol, and then up to the point it generates the hash symbol, it will simulate M2. Once this generates the hash symbol, it will switch back and compare this and this. If they are the same, it will accept. If they are not the same, it will proceed further generating. If at some stage W is input is W, if W is generated, then at that stage the comparison will say OK and it will accept. Okay. So, if L is generated by a Turing machine M2, then you can construct a machine M1 which will accept the same language. Now, the other way around, if L is accepted by a Turing machine, how will you construct M2? If the Turing machine halts on all input, one by one you can take the strings. Suppose the Turing machine halts on all inputs, it is recursive, then one by one in the standard ordering you generate the strings. A, suppose the alphabet A is A, B, C, A, then suppose L is a recursive set, then the Turing machine will halt on all input. One by one you generate a string. The strings can be enumerated. First one, suppose the alphabet is A, B, C. Then A will be generated first. You keep one tape as output tape. M2 will simulate M1, and if this is accepted, it will print here. If it is not accepted, it will take the next symbol, try that. If it is accepted, it will print. Like that you can print. But the Turing machine need not halt always. This is not true. In that case, what will happen? What happens is, see, if there is a string W, then if there is a string W, it will simulate M1, and if it accepts, it can print. But if it does not accept, it gets into a loop. What happens? It cannot keep on simulating the behavior of M1 on W infinitely, then it will not be able to do anything. See, a Turing machine can reject an input by halting in a non-final state or by getting into a loop. Suppose it gets into a loop, this also will get into a loop and you will not be able to proceed further. Okay. If it is not if it is rejected, you must go to the next one and so on. So, how do you know that? So, you cannot simulate the behavior of M1 on any string infinitely. If you start doing that, you will be in trouble. So, what this machine M2 does is, M2 has one tape where pairs of integers ij are generated. Pairs of integers, in whatever notation you can take, decimal, binary, ij you can take. It generates pairs of integers. How can you generate one by one the pairs? Unless it is countable, you cannot generate. There should be some order, right. So, how can you have the pairs generated? Suppose I have this integer grid points, the x and y coordinates represent pairs of integers. So, this is 1 1 and this is 1 2, this is 2 1 2, what is this? Let me draw the grid again, grid this here. So, this is 0 1 2 3 4, 1 2 3 4 and so on. So, this is 1 1, then this is 2 2, this is 1 2, this is 2 1, this is 3 1 3, 2 2 3 1 and so on. Take these points, integer points. Okay. So, if you want to have them as a countable set, this is counted first, then all points in this diagonal, then all points in this diagonal and so on. So, the set of pairs of integers is countable. Okay. So, which one will come first? 1 1 will come first, the sum should add up to 2 now, then sum should add up to 3, 1 2 2 1 3, then 4 3 1 3 2 2 3 1 and so on. So, that is this point, then this 1 1 1 2 2 1, then in this diagonal 1 3 2 2 3 1, the next diagonal, then the next one will be 1 4 2 3 3 2 4 1 and so on. So, the pairs of integers is countable, one by one you can generate them. So, in this tape, in one tape you generate the pairs of integers ij, I varies from 1 to infinity, j varies from 1 to infinity. After generating this, have a tape where you generate the ith string in the enumeration. Over any alphabet you can enumerate the strings using standard ordering. Suppose I take ABC, sigma is equal to ABC, how can you enumerate the strings? A, if you want to include epsilon also, ABC, AA, AB, AC, BA, BB, BC, and this is first string means second, third, fourth, fifth, sixth, seventh. So, seventh string would mean AC and so on. So, when the pair ij is generated, you generate the ith string in the enumeration, then simulate M1 for j steps. If M1 accepts what is the behavior of M1? Suppose M1 accepts Wi, then it will have it on the input tape. There may be other tapes. Without loss of generality, you can take it as a multi-tape. Similar tapes should be there here also. Then it will simulate, M1 will move on Wi, and after some steps, say j steps, it will accept, right. After some steps, it will accept. If it does not accept, it may halt in a non-final state, or it may get into a loop. Okay. Now, what you do is you generate the pairs one by one, and when the pair ij is there, you generate the string Wi. Okay. You know which is the string in the ith string in the enumeration, and you can generate that. Then simulate M1 for j steps. If M1 accepts on the jth step, not before or after, on the jth step, if it accepts, the output tape, this has an output tape, you generate Wi. If it does not accept on the jth step, then go to the next pair, next pair, that may be some I dash j dash, then generate Wi dash, then simulate M1 for j dash steps. If it accepts on the j dash steps, you generate it on the output tape. If it does not, go back to the next pair in the pair generator. So, if at all a string Wi is accepted, it will be accepted by M1 in some steps, j steps, is not it, some j, and at some stage or the other the pair ij will appear on the pair generator, ij will appear here at some stage or the other, because one by one you are going to generate. And when the pair ij is generated, Wi will be generated here, and the machine when simulating M2, when simulating M1 will accept in j steps on the jth step. So, it will be printed on the output. So, if it is accepted by M1, it will be generated. If it is not accepted, no stage you will get that ij pair, is not it. Either it will get into a loop, in which case Wi, n plus 1, all those may appear, but it will never get accepted, or if it halts in a non-accepting stage also, it will not get accepted. You will not get that corresponding ij pair. Okay. So, if a string is accepted by M1, at some stage or the other, it will be generated by the machine M2 between two hash symbols, right, and if it is not accepted, it will not be generated. So, if L is equal to Tm, then you can construct the machine M2 in this manner, right. So, acceptance and generation, in a way one machine can accept, another machine can generate the same language. Because the strings can be generated in some order, that is why it is called recursively enumerable set. The name came because of that. It can be generated by the Turing machine. Not only that, in this construction you will note that one string will be generated only once. Of course, there is no necessity in the definition that one string should be generated only once, but in this construction you will see that one string will be generated only once. The reason is you generate that string on the output tape only when the pair ij appears and Wi is generated and it is accepted by M1 on the jth step. Suppose ij plus 1 appears, then Wi will be generated, it will simulate for j plus 1 steps, but on the jth step itself it will accept it. At that time again it will not generate Wi, it will generate only when the machine M1 accepts it, when Wi is accepted on the jth step. So, one string will be generated only once in this construction, because in the general definition we are not putting that restriction. Okay. Now, in this term we can also have a nice characterization for recursive sets. L is a recursive set. Suppose L is a recursive set, then L is equal to T of M1 for some Tm M1. That means this M1 will halt on all inputs. What is the condition? If L is a recursive set, it will halt on all inputs. If and only if L is G of M2 for the Tm M2 and M2 generates the strings in L in standard ordering. Now, given M1, construct M2 and vice versa, given M2 construct M1. Now, given M1, how will you construct M2? Suppose the input, first it will take, suppose the alphabet is A, B, C, one by one it will take. First the A will be taken, then B, then C, and then A, B, A, C and so on. Each string will be taken. So, first W1 will be taken and then W1 is A of course. Then it will simulate the behavior of M1. M2 will write the first one on the input and then simulate M1. If it, see M1 will always halt, either it will accept or reject, it will always halt. When it halts, if it accepts in the output tape, you print W1. If it halts but does not accept, leave it, go to the next one. Write the next one in the enumeration, simulate M1 with this, ultimately it has to halt because it is a recursive set. When it halts, if it accepts, write it between two hash symbols. If it does not accept, leave it and go to the next string in the enumeration. Is that clear? So, in this input tape, in one tape, you will generate W1, W2, W3 etc. one by one. When Wi is generated, it will simulate the behavior of M1. M1 will always halt. So, either it will accept or not. If it accepts, it will be printed on the output tape. If it does not accept, go to the next string Wi plus 1, right. So, this is the way this works. Then in this case, if L is equal to M1, L is equal to G of M2, there exists M1 such that L is equal to T of M1. Here in one case we will not be able to really construct the machine, we only prove that there will be a machine M1 such that L can be accepted by the Turing machine. There is a subtlety here. If L is infinite, no problem. The problem arises in a special case when L is finite. So, suppose L is infinite, then in this case no problem. How does M2 behave? M2 has an output tape where the strings will be printed in standard ordering, right. So, how does M1 behave given a string W, how will M1 accept it or not? What M1 does is it will call M2 as a subroutine, keep on printing the strings here. At some stage W will be printed. This is in a canonical order, lengthwise and within the same length lexicographic order. So, at some stage W will be printed between two hashes, or some string W dash which is less than W will be printed, next W2 dash which is greater than W will be printed. If W is not in the GM2, then some string W dash which occurs before W in the enumeration will be printed, and next W2 dash which occurs after W in the enumeration will be printed. If W is in GM2, it will be printed. So, two possibilities, either W will be printed or some W2 dash which is higher than, which occurs after W in the enumeration will be printed. So, it keeps on checking, M1 keeps on checking whether W is printed or not. If W is printed, it will halt and accept. If W is not printed, after some W dash, W2 dash is printed which is comes after W in the end, that means W is not generated by the Turing machine M2. So, in this case it will halt and reject. Either way M1 will halt on the input W and say yes or no. This is when L is infinite, there is no problem, but when L is finite, suppose L is finite, there is a small problem here. What may happen is M2 can, it is say W1, it has got k strings W1, W2, Wk, finite set, it has got only k strings. So, M2 can print one by one. Now, after printing Wk, we are only saying that it will print all the strings in G of M2. There is no necessity for M2 to halt after printing the last is 1. If it halts, well and okay, but there is no necessity that M2 should halt after printing Wk. What it may do is, after printing all these symbols, it may get into a loop. It does not do anything else, it has just printed the k strings, afterwards it just gets into a loop. So, whatever is printed on the tape between two hash symbols is G of M2. So, this G of M2 consists of k strings W1, W2, Wk. In this case, that construction which you have just discussed will not work, is not it? Because given some string, say W is greater than Wk in the enumeration, W occurs after Wk in the enumeration, then neither W will be printed here, not something greater than W will be printed here. After printing W, it gets into a loop. So, in this case M1, if you follow that construction, M1 will also have to go into a loop, but if it is a recursive set, M1 has to halt really, it has to halt whether it accepts or not. If it goes to a final state, it will accept, if it goes to a non-final state, it will reject, but it has to halt. But this sort of a simulation which we consider for the infinite set will not work for the finite case, if at the end M2 gets into a loop. So, in this case we may not be really able to construct the Turing machine, but this happens only when G of M2 is a finite set, but any finite set can be accepted by a finite state automaton, and when it can be accepted by a finite state automaton, it can definitely be accepted by a Turing machine, right. So, we can construct a Turing machine which will accept just G of M2 even if it is finite. Infinite we know the construction, finite we know that we can construct a Turing machine because we can always construct a finite state automaton for this. But given M2, whether G of M2 is finite or infinite, we do not know. If it is infinite, we will be able to construct a Turing machine. If it is finite, we will not be, we know that a machine exists, but we will not be able, we cannot say that. And given M2, whether G of M2 is finite or infinite is an undecidable problem. It is okay. So, that we cannot say. It is a sort of, hereafter we will come across this sort of an argument, especially when we study undecidability, which will next class or so we shall start. Okay. So, we do not know whether G of M2 is finite or infinite. If it is infinite, we know how to construct a Turing machine M1 which will accept the same thing halting on all inputs. If it is finite, we know that a finite state automaton will always exist for that, and once it can be accepted by a finite state automaton, it can definitely be accepted by a Turing machine, right. So, this there is a subtle argument there, we have to take care of that in the proof. So, this is so far as considering the Turing machine as a generator, and we have considered generalized versions of Turing machine which are equivalent to the basic model. Now, we shall consider restricted versions of Turing machine which are equivalent to the basic model. Restricted versions of Turing machine equivalent to the basic model. One is 2 push down tape Turing. Two PD push down tape. The Turing machine has 2 tapes and both of them behave like a stack. Only the topmost symbol can be read, and you can push symbols, pop symbols and so on. So, the Turing machine has 2 tapes, and this is the top of the stack, and again another one which is the top. With this we can simulate any Turing machine. 2 tapes it has got, they behave like a stack. Stack means you can increase the stack. So, as you can print more and more symbols here by pushing. Okay. So, as many symbols you can want you can add. How can you do this? So, if you have the Turing machine and at some stage it contains A0, A1, A2, An, A minus 1, A minus 2, A minus 3 on the tape, then this is the current head position. In this one it will be represented as An, An minus 1, A naught, A minus 1, A minus 2, A minus 3 and so on. Always the second tape contains the top of the current symbol read by the Turing machine. Suppose the next move it prints a X and moves right. So, what will happen is this will print a X and then this will be transferred here, I am sorry, it goes to A1, okay. X will be A1, X will be printed here, this tape head will move right to A. If it moves left, in that case x will be x is here, this becomes, this head will be here. So, whatever manipulation is occurring, only occurring at the top, x is pushed here and this is remains as it is. Now, suppose the move is to the left, originally you had A naught here, suppose it is moved here, this is changed into x and then this is pushed on. This tape head will move, A1 will be popped off from that, A minus 1 will be popped out from here and it will be added pushed here. So, again the current symbol read is A minus 1, this. So, anything can be, any Turing machine with one tape we can simulate by 2 push down tape. Of course, a multi-tape Turing machine can be simulated by a one tape Turing machine. So, any Turing machine you can simulate with just 2 push down tape. This is a restricted version, it has got 2 tapes, but both of them are behaving like a stack. Stack is very restricted compared to the general Turing machine tape. In the general Turing machine tape, we can move anywhere on the tape, you can print symbols anywhere you want and so on. But stack manipulation will be done only on the top, either you can push or pop and so on. So, any Turing machine you can simulate with 2 push down tapes. This is a restricted version equivalent to the basic model. Then another is 4 counter machine. Can simulate any Turing machine. What is a counter machine? Counter itself tells you that it keeps a count. So, the Turing machine will have some tapes where there will be one symbol and rest of them will be blank. There will be one non-blank symbol here and rest of them will be just blank. The tape head will be somewhere here. This is called a counter. It does not write anything on this tape. The number of cells from Z, the tape head is in this cell, suppose it is at the 10th cell, the count is 10. So, you count from this Z till the head position, that is a number, is not it? So, this tape tells you that number. So, this tape gives you only the information of a number. Okay. So, we can show that like that if you have 4 counters, they are very restricted versions of a tape, is not it? It has got only one non-blank symbol, rest of them is blank. You can move left and right, does not matter, but you do not print anything. The tape head will just move on the tape. And the only information you have is the number of cells from the non-blank symbol. Where is the head from the non-blank symbol? It just keeps a count. Such a tape is called a counter. Okay. So, with 4 such tapes you can simulate any Turing machine. If you have 4 such tapes which behave as counters, we can simulate any Turing machine. How can you do that? The way you do that is like this. You know that two push down tapes, with 2 push down tapes you can simulate any Turing machine. That is what we have just seen. Simulate any Turing machine. Now, if you show that one push down tape can be simulated with 2 counters. If you show that one push down tape can be simulated by 2 counters, 2 push down tapes can be simulated by 4 counters. Now, how can you simulate one push down tape with 2 counters? The push down tape will have something like Zm, Z1, something like this, is not it? Write it as a string Z1, Z2, Z3, Zm. This is the content of the push down tape, right. These symbols come from an alphabet. Okay. So, the alphabet gamma has say x1, x2, xk k minus 1 symbol, including the blank symbol. It has got k symbols. So, this Z1 is one of the hex keys, right. Z2 is again one of the k symbols, k minus 1 symbols. Okay. So, this I would write instead of 1, 2, I will write it as Im, which will be more clear. Zi1, Zi2, Zi3, Im. Each of them will be a symbol from here. So, I1 will be say 5, I2 will be 7, something like that, is not it? So, I mean actually it is the same symbol. So, I will write it as xi1, xi2, xim. Now, you look at an integer j which is Im times plus k times Im minus 1 plus k square times Im minus 2 and so on. K power m minus 1 times I1. You are having k minus 1 symbols here. So, you take the base k and write this. Now, from j will you be able to get I1, I2, I3 etc. You can uniquely get back the string. Divide j by k, whatever remainder you get, that will tell you what is Im, what is the last symbol. Take the quotient, divide by k, that will tell you, the remainder will tell you what is Im minus 1, right. Again take the quotient, divide by k, that will tell you what is this. So, this is the content of the push down store can be simulated like this. Suppose I add XR here, I am pushing one more symbol, how will j change? J will change to kj plus r, is not it? So, in one counter I have j, then I must have, instead of this I must have kj plus r, right. I will try to have that in this step, then alternatively I can use them. Okay. So, first I have j here, I want to have kj plus r here. How will you do that? This head will be here initially, move this cell one cell to the left, move this one k cell to the right, move this one cell to the left, move this one k cell to the right. When this reaches here, this will be somewhere here representing Kj. Then move it R more cells, then you will have Kj plus R in the second tape, right. When you want to remove that, this is pushing, popping, when you pop what happens? You must have, in one counter you are having J, in this counter you must have K by J, I am sorry J by K, sorry, J by K, the floor of that, right. How can you get it? Here the tape head is pointing here, move it K cells to the left, move this one cell to the right, move this K cell to the left, move this one cell to the right. So, finally when it tries to move left of this Z, you stop. At that time you will have the quotient when J divided by K in the second tape. So, a counter is a specific kind of a tape where there is only one non-blank symbol and the head position tells you how many cells it is from the non-blank symbol, that is it gives just an integer can be stored in a counter, nothing else. And making use of that, you can show that any Turing machine can be simulated by 4 counters. The method is, you know that any Turing machine can be simulated by 2 push down tapes, and we show that 1 push down tape can be simulated by 2 counters. Now, any Turing machine we have seen that can be simulated by 4 counters, it can also be simulated by 2 counters. Any Turing machine we can simulate with just 2 counters. How can you do that? So, 4 counters we can show that we can simulate with 2 counters. So, actually the 4 counters, 2 counters are enough. Actually with 4 counters you store 4 values ijkl. You can store it by one number m, 2 power I, 3 power j, 5 power k, 7 power l. This will tell you the, from this you can retrieve back the values of ijkl, right. So, in one counter you can store this, the other counter is for manipulation. When you want to increase I by 1, you have to multiply by 2, when you want to increase j by 1, you have to multiply by 3 and so on. For that the other counter will be used. This idea is called Gdel numbering, right. So, just a little bit about more on restricted versions, then we will go to universal Turing machine and the halting problem. So, we have used the idea of Gdel numbering in constructing the counter machine. Let us see what is a Gdel numbering. This is an important concept which is the basis of Gödel's incompleteness theorem, which you know is a very famous theorem. Gödel's incompleteness theorem says that there is no complete and consistent system for integer arithmetic, or any axiomatic system for integer arithmetic has statements which are true but which cannot be proved from the axioms. For that he used an idea which is called Gdel numbering. We are also using that idea in the construction of counter machines. Now, let us see what is a Gdel numbering. First of all, let us consider the Gdel numbering of a sequence of positive integers. So, now let us consider the primes in the increasing order of magnitude. So, prime 0 is 2, this is the first prime, we call 3 as prime 1, then prime 2 is 5 and so on. The Gdel number of the finite sequence of positive integers I1, I2, In is 2 power I1, 3 power I2, 5 power I3 and prime n minus 1 power In. For example, suppose we have the sequence 2 1 3 1 2 1, then the Gdel number of this sequence will be 2 power 2 because this is 2, then 3 power 1, second number is 1, next prime is 5. So, the next sequence, next number in the sequence is 3. So, you have 5 power 3, then 7 power 1, next prime is 11 and the next number here is 2. So, 11 power 2, 13 power 1, and if you calculate this value, it is this number. It is a very large number, and given a sequence you can find the Gdel number of that sequence, which is a very large number, and given a Gdel number, this sequence can be obtained in a unique manner. From the Gdel number, the sequence can be got back. Now, for example, suppose the Gdel number is 4200, the sequence is 3121. How do you get this? This is obtained as follows: divide 4200 by 2 as many times as possible. So, 2 divides 4200 3 times and you get the quotient like this. So, the first number in the sequence is 3. Then you try to divide 525 by the next prime, which is 3, it divides only 1. So, the next number in the sequence is 1. The quotient is 175 now, and try to divide by 5 and it divides 175 2 times and you end up with 7 as the quotient. So, the third number in the sequence is 2 and the last number is 1 because next prime is 7, 7 divides 7 once. So, the sequence is 3 1 2 1. So, given a sequence we can find the Gdel number, and given the Gdel number we can find the sequence. Now, the same idea can be extended to strings, and this is the idea used by Gdel in his theorem. Once we have a method of finding the Gdel number of a sequence of positive integers, we can extend it to strings. How do we do this? Any written piece of English text you can assign a Gdel number. Now, assign a positive integer to every distinguishable character including the blanks, small letters of the English alphabet and punctuation signs. One possible way of doing this will be blank you denote by 1, small a to small z you denote by numbers 2 to 27. Small a stands for 2 and 3 stands for small b, 4 stands for small c, and so on. Then capital A through capital Z use the numbers 28 to 53. So, capital A will be 28, capital B will be 29, and so on. Then the full stop you can use number 54, comma use the number 55, and so on. The Gdel number of any piece of text is simply the Gdel number of the corresponding sequence of integers. For example, the Gdel number of the word book is this: y, b is 3, o is 16, o is again 16, and k is 12. Okay. So, the sequence of integers will be 3, 16, 16, 12, and choosing the corresponding primes you get 2 power 3 into 3 power 16 into 5 power 16 into 7 power 12. This is the Gdel number of the word book. So, any English sentence you can have a Gdel number. You must remember that the Gdel number will be a very large number. What Gdel did in his incompleteness theorem is he made a statement and the Gdel number of that statement he calculated. So, the statement was something like this: the theorem whose Gdel number is x is not a theorem. The statement whose Gdel number is x is not a theorem, and when you calculated that number it was x. So, some sort of a self-referential thing was there, and he proved that you cannot have a complete and consistent system for integer arithmetic. Anyway, we will not go into that now. Next we will see what is the Gdel number of undirected graphs. Any data structure also we can try to attach a Gdel number to that. So, let us see how we can do it for undirected graph. An undirected graph consists of nodes and edges. So, we will not consider simple graph, multiple edges can exist between two nodes. So, the Gdel number beginning with assignment of distinct prime number to each node of the graph. The assignment is made arbitrarily. So, I have a graph with 4 nodes and I am assigning prime numbers to this. So, 2 is assigned to this, 3 is assigned to this, 5 is assigned to this, 7 and 11. So, you could have given in a different way also. This assignment is arbitrary, and when we note that we have information about how many nodes there are and which nodes are connected to which by edges, we have a complete information about the graph. Supposing the nodes have been numbered P0, P1 and to Pn, because we are assigning prime numbers to them, we take a Gdel number of the graph to be the number P0 to the power K0, P1 to the power K1, P2 to the power K2 and so on up to Pn to the power Kn. For example, here we have 2, 3, 5, 7 and so on, and we will have the corresponding Gdel number. Now, when Pj is raised to xj, it is actually Kj, Kj is the product of all these numbers. What is Ki? Kj is 1 if and only if the number Pa is not connected to any other node. Consider the following graph where the nodes are assigned prime numbers. 2 is connected to 3 by 2 edges, 2 is connected to 5 by 1 edge, 2 is connected to 7 by 1 edge. So, the Gdel numbering for this graph will be 2 power k0, 3 power k1, 5 power k2, 7 power k3, 11 power k5, where 11 is an isolated point, it is isolated node. So, k5 will be 1, 2 is connected to 3 by 2 edges, it is connected to 5 and 7 by 1 edge. So, k0 will be 3 power 2 star 5 star 7, that is multiplied by 5 and multiplied by 7. K1, let us go back, 3 is connected to 2 by 2 edges. So, it will be 2 power 2. Now, K2 is connected, K2 is for the node 5, 5 is connected to 2 and 5 is connected to 7. So, we have by 1 edge. So, 2 power 1 and 7 power 1, 2 power 1 multiplied by 7 power 1, and the fourth one 7 is connected to node number 2 and node number 5 by a single edge. So, you have 2 power 1 multiplied by 5 power 1, and that is the value of K4. So, the Gdel number of this graph is given by this number, and if you have assigned different numbers for this, suppose I call this as 2 or call this as 5, then the Gdel number will be different. From the Gdel number of a graph we can get back the graph, but for one graph if we renumber the nodes we may get a different Gdel numbering. Now, we can extend this concept to directed graphs, labeled graphs and other data structures also. So, for the given graph in the figure, the Gdel number will be this much. So, thus we can have a Gdel number for all data structures defined in a suitable manner. We are using this concept in the construction of counter machines.